Okay, so in the previous lectures, what we have studied, we did S matrix. I mean, we just understood how we can construct an S matrix. Okay, that gives us actually the time evolution from some initial state, okay, to a final state. Yeah? Okay, and then okay, so then we did the Wick's theorem. Right? Okay, so the content of the Wick's theorem, what we saw, we have always arising the time ordering and the normal ordering in the given S matrix expansion. Okay, so Wick's theorem helps us to resolve that kind of, conflict between time ordering and the normal ordering. Okay, so let's try to apply these two ideas and understand how we can construct the Feynman diagram of a given process. Okay. Okay, so we will consider this one. Okay, so our main motive is to understand the Feynman diagram based on the S matrix expansion. Okay, we end with the help of the Wick's theorem. Okay, we will use S matrix and the Wick's theorem to understand these Feynman diagrams. Okay. Okay, so for that matter, we will consider this kind of process. We will consider a process into decay. Okay, we will consider a scalar particle that decays into the fermion and antifermion pair. Like this. What I mean by that, let me take a scalar boson. Okay, the quanta of the scalar boson I am saying B, and K is the core momentum vector for this very particle. Okay, I will consider its mass to be m. Or the rest mass energy, it is mc square. Since we are using C equal to 1 and H plus equal to 1, so its rest mass energy is simply what? M. So I want to consider this kind of process. So it goes to a fermion. Let me call the fermion as an electron. Okay. So we will use the terminology electron and positron. Huh? Electron means the fermion and the positron means the antifermion. So P. Okay, so let's assume they are their mass is same. Okay, so let's consider its rest mass energy to be m. So its rest mass energy is also m. We are considering this kind of process and try to understand. Okay, at the end we will be able to calculate what is the decay rate. At what rate this boson decays into a fermion and antifermion. This is our goal. But in between, we will try to understand how these Feynman diagrams emerge. Okay, or in between, we can see how we can apply this Wick's theorem to this kind of process to get the Feynman diagrams. Clear? Okay, so and I consider this process happens through a Yukawa interaction. Okay, so let's assume this process happens through the Yukawa interaction. That means it involves, my interaction Lagrangian is something. So let me write minus G psi bar psi and phi. So you are having fermion antifermion pair. That means two fields corresponding to the fermion antifermion and one field corresponding to a boson. Okay, so this kind of interaction we call it as a Yukawa interaction. Got it? And this process is kinematically possible if this mass is greater than twice. If the initial rest mass energy is larger than the sum of the rest mass energies of these two particles are equal. Huh? Clear? So then this process is possible. Clear? Okay, so have you got the idea what we are trying to do? Okay, so I am considering this kind of process where a boson decays in, think of, let's say, this pi naught particle or Higgs particle. Huh? So you are having pi naught, okay, it goes into the fermion electron and positron pair. Clear? So this is your scalar particle and this is electron and positron pair. Clear? So much, and I am assuming the interaction. Let's assume this process happens through an interaction we call as the Yukawa interaction. There can be different interactions as well. Okay, you can think, okay, let's assume this process happens through the beta decay. Okay, then you need to change the interaction Lagrangian. Okay, for the beta decay, interaction Lagrangian is different. Clear? You can think, let's assume this process happens to some arbitrary interaction. You need to use the Lagrangian for the interaction Lagrangian of that kind of interaction. Got it? Any problem? Okay. So now if I know the interaction Lagrangian to be that, then I can write this interaction Hamiltonian HI of x. So it will be like this thing. Since it does not contain any kind of derivatives, interaction will be simply negative times of this Lagrangian. So it will be psi bar psi and phi. If I normal order this thing, okay, so you need to put the normal ordering. Here, normal ordering, let me repeat it. It means put all the annihilation operators towards the right of the creation operators. Clear? Okay. So what is our S matrix therefore? So let's calculate, let's write the S matrix. Let me write that S matrix as S. Okay, so that is something time ordered of exponential minus I integral d4 of x, this hi of x. Let me put it in the normal order form. Clear? This is the S matrix what we have already obtained. Okay, so I can make now the expansion of this thing. Okay, so let's expand this exponential. What will be the first term? Let me write it on this side. Okay. So I will write this as let's take 1. What is the first term? Okay, it is e raised power minus ix. It is 1 minus ix. So I integral of d4 of x, then normal order hi of x. Clear? Then there will be the next term. What is that? Plus minus I square by 2 factorial integral of d4 of, let's say, x1, d4 of x2. 2 times the then time ordered hi of x1 like this thing. Hi of x2. Clear? What is the next order term? I require these things. Minus I cube by 3 factorial integral d4 of x1, d4 x2, d4 x3. Then you put this time ordering operation hi of x1, okay, hi of x2, then you put hi of x3 plus 1. Why I have not put the time ordering here? Because it contains only one time argument. Clear? So that's why we don't require it. Now let's forget all these terms. Let's look at this 1 first. Okay, so what 1 means? 1 means nothing. So if you are having a particle, it comes and goes and there is no kind of interaction. Okay, so that means this is not useful to us. Okay, so let's look at the, okay, so I am doing actually, if you see, it's actually a perturbative expansion of e raised power x, okay, when x is small. So much on? Okay, now let's take this very term. Okay, so much on? Okay, so let's take this term. So you are having hi of x. Okay, so let me write it as the normal. Let's write this hi of x. Clear? Okay. So what is our hi of x? G times psi bar of x, psi of x, and phi of x. So that means all these fields are defined at the same point, same space-time point, because this contains only one time argument. So only one space-time point. Now look at these two terms. These terms. So you are having some field is defined at space-time point x1 and another field is defined at x2. That means you are having field is defined at 2 points. And in this case you are having field is defined at 3 points. So much on? Okay. Now let's look at this very term and try to analyze our process. Now, okay, keep in mind what is our process. You are having a boson, it goes into an electron and positron. Forget about the momentum, whatsoever is the momentum there. Clear? So what is our initial state? So this process means you need to annihilate a boson here and then create what? Electron positron. Clear? So it means you need to figure out this kind of amplitude. You are having a boson, then you need actually in the final state what? This electron and positron. Got it? So this kind of thing, I mean, we need to construct. Or in other words, I need actually a matrix element of these things between what? Of S between these two states. So S will help us to take this B to these two states. So we are actually, if you remember, we are actually interested in this thing. I and the final state. So this is our main motivation. So this will give us this will simply provide us the amplitude of the process. And you take the mod square of this thing, that will give you the probability of happening this kind of process. Got it? Okay. So now let's look at, since and one we have ignored because it gives us nothing. Okay. So the first order term, so we call this, okay, this is zeroth order term, it doesn't give us anything. We are taking the first order term. Okay. In the first order term, I am having these kinds of fields. Clear? Okay, so and I need to construct that kind of process from these fields. Okay, so what I will do? So for that matter, I will write, okay, so let me first decompose this phi into two types of fields. That will represent the annihilation of the particle and another part will represent the creation of the particle. So let me decompose it as a phi plus and phi minus. Okay, so if you remember, you are having this phi actually in this sense, okay? So this I have already told you many times. So let me write it 2 pi cube twice EP. So you are having this A of P e raised for minus I P dot x plus A dagger P e raised for I P dot x. Okay? So this part you write as phi plus and this part you write as phi minus, including this integral. Okay, so phi plus annihilates the boson and phi minus creates the boson. Clear? This is the terminology what we have already done. And similarly, you are having this psi of x, if you remember, it is something d3p divided by root of 2 pi cube. Just for you people, I am writing it. So s means sum or simple. Okay. So you are having, if you remember, fs of p, clear? Then you are having us of p e raised for minus I P dot x plus f tilde. So s of p ds of p e raised for I P dot x. So this is actually the annihilation of fermion. So annihilation of electron, and this means creation of positron. Okay. So I will put that psi of x as psi is equal to annihilation. Let's write psi plus as the annihilation of the fermion, clear? Plus psi minus as annihilation of anti-fermion. Got it? Psi plus gives you what? So this means annihilation of fermion, and this gives you what? Creation of anti-fermion. Annihilation. So annihilation of fermion. So this means creation of anti-fermion. Okay. So similarly, I will write now psi bar as, so that will be actually psi bar plus psi bar minus. Okay, psi bar plus, if I take now psi bar plus, so let me write this psi bar of x. So it is d3p divided by root of 2 pi cube twice EP summation over s. Okay, so if you remember, it's actually f dagger s of p, rather like this thing, f tilde s of p. Okay, v bar s of p e raised for minus I P dot x plus f dagger s of p u bar s of p e raised for I P dot x. So first term will give you the annihilation of the anti-fermion. Okay, the psi bar plus will give you what? Annihilation of the anti-fermion. So psi bar minus will give you the creation of the fermion. समझ आओ? So this is annihilation of ND fermion. ND fermion, this is creation of fermion. Okay? So just remember this notation. This notation directly follows from the Fourier decomposition of these fields. Clear? Huh? Any question or any confusion? Okay, so why I am trying to decompose it in this form? Because I need a process where you can actually annihilate a boson, and then from that you create what? A fermion and antifermion pair. Clear? That's why I require this kind of decomposition. Otherwise, I cannot say, because psi is also, this psi contains fermion as well as antifermion. This psi bar also contains fermion and antifermion. So I cannot say from the field directly. What I need to do? I need to do a decomposition. Clear? Okay. Okay. So let me write. Let's substitute these things in this HI. So therefore, I can write this normal ordered of HI of x. So that's equal to G normal ordering of. So what is psi bar? Okay, so you are having psi bar plus of x plus psi bar minus of x. Put arguments, these space-time arguments. Then you are having psi plus of x plus psi minus of x. Then you are having phi plus of x plus phi minus of x. And then you put the normal. Let's multiply. So it is G. Okay. So you multiply. So what you are having? I will put normal ordering here. So let's multiply. So it is psi bar plus of x. Then psi plus of x, phi plus of x. Clear? Then what is the another term? Psi bar plus of x, psi plus of x, phi minus of x. Clear? There are 8 terms. Then you are having psi bar plus of x, okay, psi minus of x, phi plus of x. Then you are having psi bar plus of x, okay, psi minus of x and phi minus of x. Clear? Then you are having psi minus and same thing, okay, psi bar minus of x, psi plus of x. Then you are having phi plus of x. Then psi bar minus of x, okay, psi minus of x, okay, so psi plus, okay, then you are having phi minus of x. Clear? Got what, Mako? Okay, so then you are having a term psi bar minus of x, okay, psi minus of x, phi plus of x. Then and last term will be psi bar minus of x, okay, psi minus of x, phi minus of x. And you have to normal order this kind of product. Normal ordering means put annihilation towards the right of the creation. Okay, so for the time being, I will not take that. Okay, so okay, so now let's look at these very terms. So what? Okay, so let's look at this very term. Okay, clear? So what it is? So you are having, let's write this very term psi plus of x, then phi plus of x. Clear? So on the this very side you are having boson, electron plus positron. Clear? This is the process. Okay, so now what is phi plus doing? Phi plus is an annihilation operator. Clear? Is it true? So what it is doing? It is annihilating a boson. So when it acts on this left hand side, let's say you are having boson, on the right side it is like this, electron positron. Clear? So this is the matrix elements we need to evaluate actually. So it is actually this object is sandwiched is Hi of x. I am taking the first term. Okay, so this phi plus will annihilate the boson. So what you get? So you get actually, so you are having actually this phi plus acting on the boson, it is the vacuum state. When it annihilates, okay, so that way it, okay, so what I mean to say, when phi plus acts on the boson, so it will annihilate it, so you create actually a vacuum. So when phi plus x on the vacuum, again it gives you 0. So this boson means it's actually the moment, it's a single particle state, and phi plus is doing what? Lowering down the state. So it's like this thing. If you okay, so this B state is simply it's something what we call some particle state. That's right, some K state K. Clear? So when you act actually this phi plus on this boson, what it is doing? It's simply the annihilation operator. You put some annihilation operator on this K. Clear? So what it is? So it will lower down this very state by value of 1. What is the lower state? So that is the vacuum. Clear? So from the vacuum you are actually creating the particles, one particle state. This is a one particle state. Huh? Clear? I am considering only one particle. Okay. So you are having the boson. Now what you are having here? Psi plus. So you are now on the vacuum. Then you are having psi bar plus of x, and then you are having electron positron. Clear? So either they will act on this very side or they will act on this, because you are having no vacuum. Huh? You have created a vacuum. From vacuum you have to create the electron positron pair. Clear? Okay, so what you will do? So what is psi plus? It is annihilating. It is an annihilation operator. It annihilates the what? Fermion. Clear? But on this side, what you are having? A vacuum. So what it will do? It will annihilate the vacuum. When you annihilate the vacuum, what it means? So it makes it 0. So this, what I mean by that, so you are having, let's say, annihilation of the boson acting on the vacuum, it gives you 0. Annihilation operator of the fermion acting on the vacuum, it is giving you 0. Annihilation operator for this thing, annihilation for the positron. Clear? So acting on the vacuum, it gives you 0. So what it yields me? So this is simply, for this very process, this term does not contribute. Or in other words, we can think it another way around. So you are actually, this process, what you are having, it means in the initial state you have to annihilate the boson, and in the final state you have to create what? Or okay, if you look at from the left, that means you need to annihilate them as well. These operators, when they will act on left, so what you should get? You should get again the vacuum. Huh? Okay, that is another way to look. Huh? It means you are acting these operators in the forward direction. What I mean to say, if you act these on the left hand side, so what they should actually do? They should annihilate these particles. Huh? So that you will get actually a vacuum. Huh? So that vacuum expectation with the vacuum is equal to 1. Got it? So okay, so let me tell you. So what is psi bar doing? Psi bar plus. It is annihilating what? Fermion. So when it acts on the right of the state, okay, when it acts on the left state, what it will do? So think of the harmonic oscillator. You are having A acting on something, it is an annihilation operator. When this A acts the backwards, what it will become? So when this A acts the backwards, what it means? So it is same thing as the creation operator acting on the forward side. So when A acts on the cat, which is in front, so it will act as an annihilation operator. When this A acts on the backward cat, so it will act as a creation operator. So what this will do me? So this is an annihilation operator when it acts on the forward cat. Clear? But when it acts on the backward cat, what it will do? It will become a creation operator. So that means you are creating one additional particle. This is an what? Creation of the anti-fermion. So but you already have one anti-fermion here. So that means you are creating one additional particle. But the process involves how many particles? Only 2 particles in the final state and 1 in the initial state. So that means this will not give you the corrective process. So looking at these very terms, you need to figure out one term or one or more than one term which actually depicts the corrective process. So this is the simplest of way to look. So that means you need a term or more than one term which actually give you one particle in the initial state and 2 particles in the final state. Clear? Okay, so now let's look at these terms. So this we have seen, now this does not give us. Now what it means? Phi minus means what? Creation operator. So when you are having a state on this very side, it will give one additional boson. Clear? So you are having only one boson here. Got it? So that means this will also not contribute. समझ आओ? Okay. So similarly, you look at the other term. So you are having this as an annihilation operator. Clear? So you annihilate the boson. Okay. So that means you are having one particle in the initial state. But now let's look at these two terms. So you are having one additional particle in the final state, or you are having something. This will annihilate the vacuum. This will create a particle, rather empty particle, but this will annihilate that vacuum. Huh? समझ समझ? क्या समझ? So let's look at, okay, so let me take this very term. So you are having like this thing, electron, positron. So then you are having psi bar plus, psi minus, phi plus. Clear? Then you are having the boson. So this will do what? Phi plus will act on the boson, it gives me the vacuum. Then you are having psi minus, psi bar plus positron, let's say the electron. Clear? So what you get from here? Psi minus, it is the creation of the antiparticle. So you have created a positron. Clear? But what you are also doing, you are annihilating. So it is something, okay, psi, okay, so this is something E minus E plus, okay, psi bar plus acting on the vacuum, okay, tensor, psi minus acting on the vacuum. This object is like this because it's a two particle state. Huh? Okay, so this will give you the antifermion, let's say the positron, but this will give you 0. So this overlap with this will become the 0. Otherwise, you have created one antiparticle. Clear? So that means these terms will not contribute. There is only one term, this one, this very term, which is actually giving you the non-zero. So this is only the non-zero contribution. Let's look at it. Okay, so let's look at this very term. Okay, so you are having this electron, positron, psi bar minus of x, psi minus of x, and phi plus of x acting on the boson. Clear? समझ आओ? So what it is giving me? So phi plus x on the boson, what it gives me? 0. Then you are having psi minus of x, psi bar minus of x, and you are having this electron, positron. Clear? Okay. So now what it is doing? So this will create an antiparticle, and this will this will create a particle. Clear? So this is our nomenclature. Huh? So it will give me simply electron, positron. So this you will be having from here. So you will be getting a positron, but from here you will be getting an electron. So it is electron, positron. What is that equal to? 1. Clear? Rather, I should say that's non-zero. That's non-zero. This overlap is non-zero. So that means the initial and the final states are matched. Clear? So out of all these 8 processes, only one process depicts, out of all these 8 terms, only one term depicts the correct process. Got it? Okay. So now look at these very terms. So the space-time point while you are annihilating the boson, at the same point you are creating what? Fermion and antifermion pair. Clear? Okay. So therefore I will write. So any question till now? So we'll be having so the non-zero contribution, okay, non-zero contribution to S matrix at lowest order. So let's call that lowest order as S1. This S1 means the first order correction. Okay, so that's equal to minus I G. G is the coupling constant. D4 of x. Okay, H I of x. Clear? So what is that equal to? Minus I G D4 of x. So it is psi. Okay, psi minus of x, like this thing. So this is the lowest order correction. I mean the lowest order contribution towards our process. Got it? So is this already normal order? Sorry, it is 5 plus. So is this already normal order? Because you are having, so these are, so what this is? Annihilation operator. So you have to put this sidebar minus here. So समझ आओ? So when you normal order it, so it is something d4 of x. Okay. So because you are interchanging now the two fermion operators, so it will yield a plus sign. So you will have plus here, psi minus of x, psi bar of minus x, 5 plus of x. So this is the normal order. Okay. So now let's show it pictorially. Okay. So here I have not used any Wick's theorem because we are having fields defined only at one space-time point. Okay. So Wick's theorem we will apply in the next term. Okay. So what it means? Okay. So let's show it pictorially what is happening. So you are having one space-time point x. So let's call that point x. That point here. At this point, what you are doing? So in the initial state, you are annihilating the boson. Clear? So let me show the boson by the dotted line. Clear? So you are having at this very point, you are annihilating the boson. But at this very point, you are creating an electron and positron. So let me write those by these two lines. Okay. So now when you are having the initial state, it comes with certain momentum k. Okay. And the final state means you are having electron and positron. So let's write their momentum as p. So let me write it this way: electron with the momentum p, and let me write this positron with the momentum p prime. Clear? So what is the conservation rule? So the momentum should be, 4 momentum vectors should be conserved. So the conservation rule means at this very point, so the 4 momentum should be conserved. So what it means? A should be equal to P plus P prime. So any problem? Okay, so now to distinguish between, since we are having 2 types of particles, rather 3 particles are there. Clear? One bosonic particle, another fermion, and an antifermion. Clear? So for that matter, we will always denote boson by a dotted line, a scalar boson. We will denote it by what? A dotted line. And the point where you are creating or annihilating the particles, so that will denote by this vertex. Okay, so the vertex means where you annihilate and create the particles. Okay, so in other words, the vertex will represent simply the interaction. Because while you annihilate and create the particle, that means you are having an interaction. Clear? So this vertex will simply define me the interaction, okay, of the process. And I am having fermions. They are fermion and antifermion. They are actually outgoing particles. So I will put an arrow moving outwards, that if the momentum is from, let's say, past to future, the direction, so I will give it to the electron, to the fermion. So in this very diagram, okay, that I forgot to mention, so time is running in this direction. So you are coming from past to future. It's not the usual sense, that means from left to right. Got it? So the k is in this way, and when the electron leaves, okay, the interaction, where it will go? It will proceed towards future in the increasing direction of the time. So I will show the momentum vector as this arrow. So this is the direction of the momentum. But if you look at the positron is actually the antiparticle of the electron. So we should have actually the direction of momentum opposite to this electron. So I will put an arrow opposite to this thing. So if you look at this arrow, it is moving out of the vertex, and this arrow is going into the vertex. Okay, so these represent the initial state, these are what? Final state. This does not mean positron is moving towards the vertex. It means actually positron is leaving the vertex. So remember this very rule. So when you are having, let's say, the initial state, the particles will go towards the vertex, and in the final state, particles will leave the vertex. But a difference is, so in the final state, let's say if you are having electrons and positrons, you will show electrons and arrow leaving the vertex, and for the positrons, you will show an arrow moving towards the vertex. So if you look at the continuity of the arrows, so what is the continuity of? This is the continuity of the arrows. At the vertex, the continuity of the arrows must follow. So do you see that there is a directional continuity? So you are having actually this is the continuity of the arrows. So you cannot put actually arrow it in this direction. Then the directionality breaks down. So समझ आओ? Okay. So it means this positron is moving towards the vertex with the momentum -v. So this is the simplest of the Feynman diagram. We call it as a tree level diagram. Clear? So what a Feynman diagram means, it just depicts a given process where you have an initial states and final states represented by different kinds of the lines, and these lines met at a vertex which represents the interaction. Clear? So it's simply the graphical description of the process. Okay? Any problem? Any question? Okay, so now let's go to the next order term. What is the next order term? Let me write that order term as S2. So that's minus I square by 2 factorial. Okay, then you are having d4 of x1, d4 of x2. Okay, so G is not here. G is here because G is contained in HI. Huh? So you are having normal ordered of HI of x1 and HI of. So you can put the overall normal order, no problem. Okay, so let me write it. So it's minus I square. We are just learning the diagrams. I am not giving you the calculation of a process. That we will do in the next lectures. So d4 of x2. So this, what is H? It is G times. So you are having G square coming out. So it is some psi bar of x1, psi of x1 and phi of x1. Okay. So this comes from the first term. Okay. Then you are having psi bar of x2, psi of x2, phi of x2. And there is a time ordering as well. So we need to time order. Now let's look at this term, whether this contributes to our S matrix or not, whether this represents the given process or not. Okay, what is our process? B goes to, so that means I am having 3 particles. Okay, when you are having 3 particles in the process, so it means how many fields you require to describe this process? 3 fields. Look here, how many fields I have? 1, 2 and 3. Clear? Okay. So how many fields are in this very order? 6 fields. So 3 field is defined at point 1 and 3 field is defined at point 2. Total are how many? 6 fields. Clear? Out of these 6 fields, how many I require? 3 fields to describe the process. How many are remaining? 3. So now these 3 I have to apply the Wick's theorem, Wick's contraction. So in general terms, you need to pair up the fields. To remove the additional fields, you need to pair up. You need to make the pairs of these fields. So how many possible pairs are there of the remaining 3? So there is only one possible pair. You can pair only 2 fields, one will be remaining. So let's say you are having 3 fields. These describe, let's say, the particle. The interaction. How many are remaining? So you pair. So you can pair this thing. Okay? Of the same nature, the fermion fields. And what is remaining? One field is additional. Clear? So that means okay, so what it means? So when you take the expectation value between this B state and this electron positron like this thing, so you will be having one additional field. So that will create one additional particle. So that's not there. So that means this will not describe your process. So this does not give any correction to the process. To the S matrix. Sorry. Clear? Okay, so let me take the other even order. Let's take the 4th order term. So that will be more clear. In the 4th order term, how many terms will be there? 12 terms. 4 times 3, is it? So that is 12 terms. Out of 12 terms, how many you require? 3 for what? Okay, so those who are not present in the last lecture, what I mean by that, when you pair the fields, it gives you a scalar quantity. It does not remain a field, clear? So it gives us a propagator. This we have seen in the Wick's theorem, okay? So there is one additional field then. So now let's take the other even order, that is the fourth order. It contains how many? 12 fields. Out of 12, how many I require? 3 fields I require for the process. What are the remaining? 9 fields. I can make out of 9 only the 8 can be paired up, because out of odd numbers only the even can be paired up. 1 is remaining, is it? This one field gives you the additional particles in the process, but your process contains how many? Only 3 particles. So that means the even orders does not contribute to this very process. Samasha? Here you have applied this Wick's theorem. I mean, you cannot contract all the fields which are remaining. So it means the even orders under Yukawa coupling, because we are considering the Yukawa. If I consider it under the beta decay, you will see odd does not contribute, but even will contribute. Okay? So it all depends upon how you choose the interaction. Okay. So even orders do not contribute to S matrix. Clear? So we have done at the first order. Now let's look at the other order, which is very non-trivial. Okay, so let's take that is the third order term. Clear? In the third order term, how many fields are there? In the first order, there were 3 fields. It described the process. In the second, we have seen it does not. In the third, how many are there? 9 fields. Clear? In 9 out of 9 fields, 3 you require for the given process. But how many are remaining? 6. 6 you can pair up. So there will be no additional field. Clear? So you can make pairs out of the 6. So that means all the odd order terms will contribute to the process. So the first non-trivial, contribution to this S matrix will come from the third order term. Let's check that. So, is it clear? Then HIR X3. Clear? So what it gives me? I cube is how much? Minus plus so it is 6. Yeah. So you will be having G coming here. So it is G cube. So G4 of X1, G4 of X2, D4 of X. Now there is a time ordering of what? Yes?
Plus or minus?
Yes, there is minus is sitting outside. Okay, so this will be something psi bar of x1. Okay, psi of x1, phi of x1. Okay? Clear? So then you are having another psi bar of x2, psi of x2, phi of x2. Then you are having what? Psi bar of x3, psi of x3, and phi of x3. Clear? Now let's, okay, for the given process I need to contract all the fields, clear? Except 3. So now let apply Wick's theorem. Okay, so we apply Wick's theorem. Okay, so Wick's theorem says for the time ordering, you take first the normal order of all the this thing, then all the single contraction, then double contraction, and so on. Clear? Now look here. If I take normal order, first term will be normal ordered. Clear? Which on the extreme right there is annihilation, and the extreme right there is creation. That will not contribute because annihilation will annihilate the vacuum. Clear? So much on. And now let's take the another terms which contain only single contractions. When you take the terms which contain single contraction, how many fields are remaining? out of 9. You take single contraction means only one pair. Samajh? Only all the possible one pairs. How many are remaining then? So then you are having 8 fields. So but your process is having only how many particles? 3 particles. You require only 3 fields. Clear? So that means if I okay, so next term would be double contraction. I mean 2 contractions simultaneously. Clear? So still there will be remaining fields. But you need to take only how many? You need to pair up all the fields except 3. So what I mean by that? So for the I mean only the non-vanishing terms will come if you pair up all the 6 fields except and 3 you keep for what? What you keep 3 for? The process. So okay, so it will be something psi bar. Okay, so let me write psi bar psi phi at x1. Then you are having psi bar psi phi at x2, psi bar psi phi at x3. Clear? So it means I need to take the contractions. So let me check how I have done which kind of terms I have taken first. So because that will help me. Okay. So what I have to take? Okay, contraction means okay. So let me write this psi bar psi phi. Okay, at x1, psi bar psi phi at x2. Then you are having psi bar psi phi at x3. So let's take. So there are how many possibilities? There will be many possibilities. Many. Okay, so you have to contract the 6 fields. I mean 3 pairs you have to make out of these fields. So there will be many possibilities. One of the possibility will be like this thing. You take this psi and contract it with this very psi bar. Take this kind of pair. Okay. Then you take this psi bar and contract it with this psi. Or this way, sorry. So let me contract it with this thing. This very psi. Clear? And then I contract these 2 phis. So this one possibility. Clear? So I will use the way I have done on my notes. Okay, so you can do all the possible. So what would be the next step? How many are remaining? Now tell me. So phi at x1, psi bar at x2, and psi at x3. So you have 3 fields. Clear? So you need to keep 2 psis. I mean, one psi bar, one psi, and one phi. Clear? So much of 3 fields that will give us the process, because we have seen psi bar psi phi gives us the process. So and in the first order term we have seen psi bar psi phi is actually equal to psi bar minus psi minus phi plus. Clear? So that gives in reality that gives the process. Clear? Okay, so rest you need to pair up. Now tell me what could be the another pair. So you take the pair. So let me. So why? Okay. So this x1 is very necessary because all these fields are defined at different points. Okay. So you are having psi bar psi phi. Okay. So you are having psi bar psi phi. Okay. So everybody have got the idea what I am trying to do. Everybody has got the idea, plus all the possible terms. So let me write this thing. This psi and psi bar. Let's take this psi bar and psi and take this phi and phi. Clear? Or you can, okay, so let's contract it like this way. So let me take this bit. So okay, so home assignment will be to make all the other possible contractions. So that will be the home assignment. Home assignment will be to do all the possible possible contractions. Possible contractions. Okay, I mean 3 pairs. Keeping 3 fields as such. 3 fields psi bar, psi and phi as such. Okay, so take psi bar, psi and phi, keep them as such, and rest you do the contraction, all the possible contractions. Okay, and check how many are there. So now let's try to understand the first term. तो समझ आओ? Clear? So let's try to understand it. If you have any problem here, just tell me. Because okay, if you understood this very term, then it is very easy to do the Feynman diagrams. Clear? Huh? Any question? Okay. Okay, so let's look at this first term. So what is our first contraction? Okay, so let me call this as A. So our A is equal to, so let me write it. It is something psi bar psi phi, okay, at x1. Let me put it here. Psi bar psi phi at x2. So after this very thing, I will stop. So you are having this psi bar and psi. Then you are having this psi and psi bar probably. Yes. Then you are having this phi and phi. Clear? Okay, so what I am doing? Contractions. Clear? Contraction means you are making the pairs. Okay. So now look here. So when I make the pair of psi bar with psi, okay, I want this psi in front of here. Huh? So you, in other words, we can say they are marrying each other. They should be, close to them, close to each other. So what I have to do? That means I need to displace this psi to this very position. समझ आओ? How many positions we have to displace it? So when I will take this psi to this thing, so it encounters psi bar here, clear? And you know fermion fields anti-commute, is it? So when I take it from this very thing, so I will yield a minus sign, clear? And now, so it will reach here, it will go to the phi field. Phi is a different than psi, okay? So they commute. Phi is a boson and psi is a fermion, so they commute. You don't have a minus sign. When it comes from here to here, and you need to interchange it again, what you will get? Minus again, clear? So that will make it a plus. So it will be something, okay, psi bar at x1, and then you are having psi at x2. This kind of pair, is it? Now look at next pair. You are having psi here. Now this psi has gone. Clear? Is this psi gone? Because this psi we have taken here. So how many fermion fields are, okay, now displace this psi bar. Psi bar has only this psi bar, clear? So it will yield me what? A negative sign. So let me write it here, okay, minus sign, okay, then you are having the psi of x1, psi bar of x3. Clear? Now, समझ आओ? Got it? Okay. So now what remains there? You are having phi of x2 and phi of x3. So phi field is no problem, huh? Can't, because bosons can go anywhere. Huh? Okay, so they don't change the sign. Huh? I mean they commute. Okay, so what remains next? Tell me. So you are having phi field at x1. So you are having phi at x1. Then you are having psi bar at x2. Then you are having psi at x3. These are the remaining fields. You need to normal order them, huh? Because there is a normal ordering sign. You have to put them in the normal ordered fashion. Clear? So समझ आओ? Okay. So you are having this minus will come out. So you are having minus 1. Okay. So when I need the contraction, the fermion propagator is some psi and psi bar contraction. I want to put it in the form of what? Psi and psi bar. So this will yield me minus 1 again. Okay. So it will be something psi of x2, psi bar of x1. Clear? So I have not put actually the these indices, I mean the similar indices on them. Okay, for the time being, let's ignore those similar indices. At the end, we will put them. So this will be something psi of x1, psi bar of x3, okay, and phi of x2, phi of x3. Clear? So now out of this very thing, what contributes? We have just seen this in the first order term, is it? So which is the term which will contribute? So out of this thing, okay, we need to see. So it is something psi bar of minus. Okay, this is the psi bar, is it? So what is the time argument? X2. So it is X2. So you are having psi minus, so argument is x3. So then you are having phi argument is, sorry, phi plus x1. So this is the term which will contribute. Okay? So and I have done normal ordering. That's why I have put this psi bar here and then psi here. Clear? Any problem? Now let's draw it diagrammatically. Okay. So now tell me what phi plus is doing what? Annihilation of the boson, and this is creating a particle, and this is creation of the antiparticle, and this is creation of the particle. Clear? So let's draw this very thing. Okay. So you are having where all these processes happen. I mean, all these things happen at different points. One at annihilation of the boson. Let's say at x1. So you are having x1 point. There you are annihilating what? Boson. So since I am taking time from left to right, okay, so this is the initial state. The line is on the left of the vertex, I mean this dot of the initial states. Clear? Okay, so now where you are doing? You are creating at other 2 points. Let's say you are having 1 point here, 1 point here. So let's call psi minus bar. So it is the x2 point. So while you are actually creating the electron in the momentum p, let's say, and at this point you are actually creating the positron. So समझ आओ? Everything at what? So there isn't any connection. No, there is a connection. The contraction terms, is it? So now tell me, there is a contraction between x2 and x3. Clear? So points, what kind of field is there? So in the last lecture, when we are doing the Wick's theorem, I told you these contractions actually represented the propagators of the fields. Clear? So this will represent the propagator of the boson field. Clear? The Feynman propagators, and this will represent these two are representing the Feynman propagators of the fermion fields. So in other words, okay, now let's look at the x3 and x2 point. Okay, so look at, there is a contraction, is it? So that is this. Okay, so let's show it as a dotted line. So now we have connected it. So then you are having actually a contraction between x2 and x1. Clear? So show it as the solid line, because these are the fermion fields, and then you are having a contraction between x1 and x2. So this is a typical Feynman diagram with one loop. Okay. So these are the propagators. They represent. Okay. Now look here. What lines are the external lines? This line, this line, this line. They are the external lines of the diagram. What are these lines? They are inside the vertices. Okay. We call these as the internal lines. Internal lines of the diagram represent the Feynman propagators. Clear? Okay, so now I will put an arrow in this way, and here I will put it in this way. The arrow on a fermion propagator goes from psi bar to psi. Okay? So where is psi bar located? At this very point. Look at the first term. Psi of x2, psi bar of x1. The direction of the arrow goes from where? Psi bar to psi. So psi bar is here, psi is here. So this is the direction of arrow. In the next term, where is psi bar? Psi bar is at x3 and psi is here. Clear? So this is the direction. Clear? Okay, and we will see these things represent. Okay, there is no arrow on the boson line. And the conservation, so if this is k, this is, let's say, p, this is p prime, conservation of the momentum should follow at where? At the vertices. Okay, now look here. If you look at the term, we are actually at the third order of the perturbation. In the very first term, we are having only one vertex line, and the vertex and the two lines going. Clear? So that showed you the first order perturbation. Now here we are having how many vertices? Three vertices. It's actually the third order perturbation. Clear? And we are actually at the third order of the S matrix expansion. So we will see actually these represent as the virtual particles. So this is actually the bosonic particle, and these are actually the fermionic nature. And okay, why? Okay, let me tell you. So they do not satisfy the energy momentum relation like this. Suppose if you are having a relativistic process, so this is the energy momentum relation. So if this is followed, it means they are on-shell particles, they are the real particles. So they can be either initial or the final state. If this is not satisfied, we call them as off-shell particles. Those are actually these lines. समझ में? Clear? समझ में? Okay, so we will proceed. Okay, so take the other term which I have written here. So draw its diagram. समझ में? Okay, so it will be now the assignment for you people. Draw the all possible diagrams corresponding to the contractions what you will get. Corresponding to the terms. समझ में? Just sit at your place today and do it. I mean, just do it. Nobody. Okay, so you don't know. At least you can try. You can put try. I mean, you don't need to know the fields, but you need to actually try it. And just pair up the fields and show you are having different kinds of diagrams. This will be one of the possible. Another you will see one certain diagrams where certain legs are out of the diagram. I mean, they will be disconnected. One part will be somewhere and another part will be somewhere. Clear? Some will be actually of this form while all the lines are connected. So we call these are the connected diagrams. Clear? Okay.